In this lecture, we will be discussing on mechanical properties of materials. We'll see the tensile test, torsion test, compression test, and finally we'll be discussing on generalized Hooke's law. So let us start with the tensile test. Now let's make it big so that we can see the tensile test demonstration. And okay, so here you can see this is the tensile testing machine. This is the tensile testing machine where with the help of the grips the tensile force is applied on the sample which is placed. You can see that how the sample is held between the grips, and this is a brass sample, and you can see that gradually the load is increasing. As you can see, the load in Newton is gradually increasing, and here you see the deformation along the axis, that is in millimeter. So here in this graph it is plotted along the x-axis, it is basically the deformation, and along the y-axis it is the load that is applied, the tensile load that is applied. So the load which is applied like this on the sample. So that is why this is called the uniaxial tensile test, which is coming on this member, this sample, and we are observing its deformation. So from this load elongation diagram, it is possible to get the stress strain diagram. Now let's see carefully this experiment. Here you can see that the elongation, this is a ductile sample, and that's why you can see a lot of plastic deformation that is taking place. So this is how we get the load elongation diagram directly, and hence the stress strain diagram. And see carefully. Now see carefully at the central region, the necking has started. Suddenly the cross-sectional area is decreasing where at a very high rate, and you see finally it fractures. Similarly, if we see the stress, the same experiment, the tensile test on a carbon steel, 0.5% carbon, 0.4% carbon is there in this steel. So this is basically a ductile material again, and you will find that this is the stress strain diagram. If you just increase this scale, then it will look like this. Okay, so from here you get some idea that how we can now there is another setup slightly different, which is also very common, where the mechanical extensometer and all that is there. You see,
using chalk mark.
So here you can see this experiment. This is the typical sample. Initially the diameter is measured, which is required to calculate stress from the load, and you can see that this is what is the initial gauge length. You can see the two chalk marks, that is what is the gauge length, and we actually measure the elongation of the gauge length. The center marking is done, and after that you can see two other marking to set the extensometer position. Extensometer is a device to measure the elongation. It's a mechanical device, and you can see in this setup it is fixed. Now the sample is fixed like this, and then extensometer is to be set, and here you see the extensometer is set exactly at the middle to measure the elongation mechanically. And this particular dial actually gives the reading of the load that is applied, the tensile load that is applied on the sample. So the basic procedure is exactly same. In a similar manner, here also you can see actually the extensometer is taken out just before necking, and after that you see that neck formation, and then it will break. Okay, so we have seen that the testing procedure. Now coming to the fracture. Finally, when the material fractures, we will observe generally ductile fracture, which is observed in case of commercially available ductile materials, and you can see this fracture surface is a typical cup and cone formation. Here you can see this is the cup part and this is the cone part. So this is a typical cup and cone formation. So here you can see that initially around 45-degree angle is there, and after that there is a region where some fibrous kind of fracture that takes place. On the other hand, you will find in case of brittle material the fracture that is taking place which is perpendicular. Okay, so exactly along this cross section. So these things can be explained, that we know that in case of ductile materials are generally weak in shear, so their failure takes place because of shear. So if we draw the Mohr circle under uniaxial load, the Mohr circle look like this. Since it fails under shear, ductile material fails under shear, and you can see the maximum shear that is taking place at this location, and which is nothing but in the Mohr circle it is 90-degree away from the axial direction. So 90-degree away in the axial direction in Mohr circle means it will be 45-degree. So that is why this initial 45-degree angle in which the fracture takes place, and because of the impurities and other things present within the material, and that is why this kind of fibrous things happens because of the plastic deformation and the hard impurities present within this material. But if you take a pure ductile material without any impurities, in that case probably you will find almost this kind of a fracture. Okay, so in that case you will find a total 45-degree angle fracture. In case of brittle materials generally the crack propagates because of the tensile force, and here you can see in this diagram the maximum tensile force is at this point, so which is nothing but this particular cross section. Okay, the area on which the maximum tensile stress which is acting. So that is why the fracture taking place along that surface. Now let us try to understand the stress strain diagram that we have just seen, the different regions. So first we will see this particular region, which is the elastic region. You see in the elastic region it is almost straight line. So elastic region means if you unload the force, again it will come back to the initial position, as you can see here. So this region is the region on which during the design of any design problem we will always keep our loading within this region. Okay, we do not want any deformation. So for the ductile materials or for the ductile materials, the failure means its plastic deformation. So to avoid plastic deformation, we always keep our design such that because of loading the stress that is developed within the component should be in this region. And you can see that this point which is called the yield point and the corresponding strength is called the yield strength. So up to this point we will consider the material to be elastic. So this is what is the consideration by the material science engineers. Next, here you see that the plastic deformation process starts. Here you see this particular region where the uniform plastic deformation takes place, and at this location in the engineering stress strain diagram the maximum stress occurs, and this point is called the tensile strength of the material or ultimate tensile strength of the material. Okay. Now finally we will see the last part, and during that the necking occurs. That means where the fracture is going to take place, suddenly the area reduction rate increases at a very high rate. As you can see, look carefully the diagram as well as the actual position, you see the neck formation and finally fracture takes place. Okay, so non-uniform plastic deformation takes place, and this particular region is called the necking, and finally the fracture takes place. The important strength quantities that we can get out of it is yield strength, ultimate tensile strength, and the fracture strength of the material. Now next, in the engineering stress strain diagram we will try to define the different terminologies that is used. Basically there are many different mechanical properties. Let us try to understand each and every term one by one. Okay, so first is what is elastic deformation. Now see, elastic deformation is a deformation that is created because of some load which is applied, but if the load is removed, then again the component of the material will come back to its initial shape and size. Okay, that means this process is a reversible process. Okay, so this particular region is basically the elastic region, and generally we consider up to yield stress, this is the region. Okay, so this particular region is the elastic region. We consider that yield point, we consider this yield point is the point up to which the material is elastic. You may heard of the elastic limit or the proportional limit, the different terminologies, but material science engineers, we consider it is the yield point because truly speaking, this elastic limit or other points, these cannot be observed very clearly in the materials, and that is, but yield point in low carbon steel materials specific, if you see the low carbon steel material, you will find this kind of demarcation so that yield point can be easily identified. But in a typical ductile material, as you can see in this diagram, the yield point is not clearly visible. So in that case, what is done, 0.2%, 0.2% proof stress is drawn, which is basically a line which is drawn, which is parallel to the line which is tangent at the origin of the stress strain diagram in that region, in the elastic region. So and where it cuts the main stress strain diagram, that point is considered as the yield strength of the material. That point is considered as the yield point of the material, and this particular corresponding strength is called the yield strength, or sometimes called the proof stress, corresponding to 0.2%. Okay, so this is a standard procedure. If yield point is not clearly visible like low carbon steels, in those materials, most of the ductile materials, this kind of visibility is not there. So in that case, corresponding to 0.2% or 0.1%, this kind of yield point is defined. So we have understood that up to this region, if the load is removed, then material will come back to its initial shape and size. So that is why it is a elastic deformation. Now we have understood what is yield strength. Remember, yield strength is a constant of that material, and it indicates about the hardness of the material, how hard the material is, because it is the point after which the plastic deformation of the material starts. So if the yield point is high, that means the material is respectively hard material, because its plastic deformation will be difficult, because yield point indicates that where from the plastic deformation will start. Okay, so yield strength basically directly gives you an idea about the hardness of the material. Now remember, the strength of the material is something which is constant for the material, and the stress is defined at each and every point, because it depends on what is the load that is applied. But the strength does not depend that what load is applied. Strength depends on only on the material. It's a material property. Strength is a material property that corresponding to either yield point or corresponding to the maximum stress in the engineering stress strain diagram. Okay, so these are certain constants. So strength is certain constant for that material, okay, and gives some property. So these strength is basically the property of the material. So yield strength is a very important property. And what is the significance of the yield point? You have understood that significance of yield point is where from the plastic deformation starts. Okay, and what is the significance of yield strength? The significance of the yield strength is that always during the design we try our stress value below the yield strength, or you can say that yield strength gives an idea about the how the hard the material is. If the yield strength is high, that means the material is a hard material. Okay, next thing we can see is the working stress. So let us try to understand what is working stress. Just now I told you that for the design purpose we always try to keep our stress coming on the component because of the loading below the yield strength. Why? Because from yield strength, above yield strength, basically the plastic deformation starts, and we do not want plastic deformation, because plastic deformation is considered as the failure for the ductile material. So to avoid failure, to avoid plastic deformation, what we have to do for a design of a component, we consider that the yield strength value, okay, the yield strength value, and we divide that by some factor of safety, and this factor of safety is a quantity definitely which is less than which is greater than one quantity, so that this quantity is less than yield strength. Okay, and this is what is called the working stress. Okay, so this is the working stress or the design stress, and based on which the design is considered. Okay, next we will consider the Young's modulus. Okay, so let me erase some of the things. Okay, so let us try to understand what we mean by what we mean by the Young's modulus. Now Young's modulus is again a mechanical property that measures the stiffness of the material, What is the meaning of stiffness or the rigidity? Stiffness, rigidity, these are the same words. Okay, stiffness, rigidity are the same words. What is the meaning of stiffness or rigidity? Stiffness or rigidity means that gives an idea about the resistance to elastic deformation. So for the elastic deformation, if you require a huge amount of load, that means the material is very stiff, very rigid. Okay, and Young's modulus is the measurement of that. So if the Young's modulus is the parameter, if the Young's modulus is very large, that means the material is very rigid. Okay, and if the Young's modulus is small, that means the material is not so rigid. So Young's modulus is measured by the slope within the elastic region. So this particular slope, here you can see this slope, if you measure, so this tan of theta is measurement of the Young's modulus. Okay, so Young's modulus you have understood, and it is the measure of the stiffness, and the meaning of stiffness is what? Resistance to elastic deformation. Okay, now next we will see resilience. Resilience again is a property of the material, and that is the amount of energy that is absorbed within elastic limit. So within elastic limit means we already know that it is up to the yield point. This point, up to this point, up to yield point, we are considering the material to be elastic. So what is the amount of energy that is absorbed up to elastic limit is basically the area under the load elongation diagram up to yield point. But in case of stress strain diagram, this unit of this quantity will be what? That is energy per unit volume. Okay, so energy per unit volume. So this is, you can say that modulus of resilience, or you can call resilience with a unit energy per unit volume. But basically the idea is amount of energy absorbed up to elastic limit. So what is the significance of that? Significance is that this much of energy always can be recoverable, because within elastic limit we know if the external load is removed, then that energy can be recovered, right? So resilience is a very important property in certain design. In certain applications we need material to be very resilient, like in case of a shock absorber we use the springs, and spring material should be highly resilient material, and you can understand that the area should be large to make it more resilient. And if the stiffness is very high, suppose the stiffness of a material is very high, in that case what will happen? If the stiffness is very high, in that case the slope will be very stiff, and in that case you can understand the area will not be very large. So you can understand, to make it a resilient material, what is required, that stiffness should not be very high, rather stiffness should be small, whereas the material has to be resilient. And stiffness again for a resilient material should not be very small, otherwise again the area will be very small. So for a spring design, you remember the two parameter. One is that modulus of elasticity should not be very high, and material should be resilient material. One of these such material is the beryllium copper, which is suitable for this spring. Now coming to the next property, that is okay, the plastic deformation. We know plastic deformation means it's a permanent deformation, and permanent deformation starts after yield point. Okay, so when your load is such that the stress within the material cross the yield point, in that case along with the elastic deformation, the plastic deformation starts. So at this point, if you just at this point if you just simply let us consider you have loaded the material up to this point. So you know that already you have gone to the plastic region, because from here to here this particular region, you can understand this is a uniform plastic deformation region. And suppose you are at this location. Now at this location, if you unload the material, then what will happen? If you unload the material, then some amount of deformation, remember, some amount of deformation will be recovered, and that is like this. So this much of deformation, this much of strain, that will be recovered. Okay, that is what is called the elastic recovery, and this line will be exactly parallel to this particular line or this particular line. So they are parallel lines. Okay, and the slope is what? The slope is modulus of elasticity. So this deformation is the elastic deformation part, so that will be recovered. Okay, but you can see that this portion of deformation, which is a permanent deformation or plastic deformation, this part is plastic deformation. Okay, so this much is recovered, but you can see that if it is in the plastic region, then even after withdrawing the external load, it will come back along this line. That means a permanent deformation is still there. Okay, so that is why this is called the plastic deformation. Then you see the next term is the tensile strength. Tensile strength is the maximum value of the stress in the engineering stress strain diagram, and you can see this particular point is that. So this is what is called the tensile strength of the material, TS. Basically it is the ultimate tensile strength of the material, but if nothing is mentioned, only tensile strength is specified, that means it is the corresponding to the ultimate point. Okay, yield strength is also called that tensile yield strength, because all the data that we are getting from the tensile test, but only by tensile strength we basically mean the ultimate tensile strength. Remember, this is also a very important design criteria, because I told you that yield strength divided by factor of safety is used to calculate working stress, but many times it is the tensile strength of the material or the ultimate point strength divided by the factor of safety is also considered as the working stress. Now next is work hardening or the strain hardening. Okay, let us try to understand what we mean by work hardening or strain hardening. Now by work hardening or strain hardening means in the plastic region, you see in the plastic region, let us consider at this location, if you unload, then the unloading line will follow this particular line, and we have already seen that some amount of elastic recovery, this is the amount of elastic recovery that will take place, but this amount of plastic deformation is still there. Now after that, again if you do the tensile test on that material, okay, then what will happen? Then you will observe that it is excuse me, it will follow this particular line, and up to this point it will be elastic, and then the plastic deformation starts. So which means that now the yield strength has been increased to this location. So previously its yield strength was this. Now after this much of plastic deformation, now the material is behaving in a different way, and you can see that its yield strength has been increased to this point. So yield strength, I have already told you, gives an idea about the hardness, because the yield strength is the amount of stress that is required to initiate the plastic deformation and hardness is basically kind of measurement to resist the plastic deformation. So you can understand that the material becomes hard. So what is actually happening? Because of the permanent deformation, materials gradually become more and more hard. So that is why this is the region where the material is actually becoming more and more hard because of the plastic deformation, and that is why this region is called the strain hardening region. So this region is what is called the strain hardening region or the work hardening region. Okay, so this thing happens in this region, the strain hardening. Now next we'll see the necking operation. Necking portion already you have seen during experiment. After reaching the ultimate tensile strength, if the deformation is taking place at the same rate, you will find that even under lower load the continuous deformation will take place at the same rate, and you will observe that material will ultimately fracture at this location. And during that, basically what is actually happening, you have seen that a particular portion, this kind of a neck formation start, and finally it fractures. So this part is what is the necking. So necking is a portion where drastically the cross-sectional area is decreasing. Next is the fracture strength. Fracture strength is basically the stress corresponding to the fracture point. Okay. Now next we can see there is a toughness. So toughness is again a mechanical property which measures the amount of energy absorbed up to fracture. Okay. So now up to fracture, what is the total amount of energy that is absorbed, that is measured in toughness. So toughness here, if we consider this area, then what is the unit of toughness? It is measured in joule per meter cube, because area under stress strain diagram indicates energy per unit volume, or toughness also can be measured in terms of joule. But the basic idea is the amount of energy that is absorbed per, either it is expressed in per unit volume or energy up to fracture. That is the important thing. And toughness is a property which is a combination of the ductility as well as its strength. And you can understand, if the material is if the strength is not very high, maybe the material is very ductile, like in case of a rubber kind of a material, they are not very tough because their strength is not very high, okay, but they are very ductile. On the other hand, if the material is very brittle, in that case again you will find that for a brittle material this total energy is very small. Okay, so that is also not a very tough material. So for a very tough material you require strength as well as ductility. Now the fracture surface that we'll see in the next slide. Now percentage elongation and percentage area of reduction. So these are the two parameters which are used to quantify ductility. So we have not yet defined what is exactly ductility. We have some idea that what ductility is. Ductility is kind of how soft the material is, but truly speaking, ductility is with respect to tensile test. Okay, so if you apply the tensile load on a sample, then how easily you can elongate that particular member, that is what is the ductility. So again, it is measured with respect to percentage elongation. So if the initial length of the sample was L0, and finally after fracture, if we see the length is L final, then percentage elongation is defined as LF minus L0 with respect to the initial length into 100%. So this is what is the percentage elongation. Percentage area reduction exactly in a similar way. If the initial area was A0 and if the final area is AF, this AF is at the fracture cross section, and that divided by A0 into 100%, that is what is the percentage area reduction. Okay, so and this is what is the percentage elongation. Both are measure of the ductility. If the material is very ductile, ductility means that there will be a large amount of plastic deformation. So large amount of plastic deformation before fracture. Whereas if you compare in case of a brittle material, so it is fracture here, and you see the plastic, you can see the deformation or the strain is very small. On the other hand, in case of a fracture, you see the deformation is very large. Okay, so here you can understand that this is a ductile material and this is a brittle material, because the strain up to fracture, if you just compare, you get an idea. So percentage elongation, percentage reduction are the parameters to measure the ductility. Now coming to the elastic recovery, already we have discussed what we mean by elastic recovery, that after elastic point, if at any point if you unload the material, it will follow the line corresponding to with a slope of modulus of elasticity, and this particular deformation, which is the elastic deformation present, that is recovered. Okay, so this is what is the elastic recovery. What is the difference between ductility and the malleability. Malleability is also indicates that if the material is very soft, then it will be malleable, but the difference is that ductility is with respect to the tensile load and malleability is with respect to the compressive load. So if you apply the compressive load and if you can make it very thin sheets without any crack, then it is a malleable material. Okay, so the difference is basically ductility is with respect to tensile load, how much you can elongate under tension. So that softness is ductility, and malleability is under compression, how thin you can make the material without any crack. So now we'll see the true stress strain and engineering stress strain diagram. In this diagram you can see that this is the typical engineering stress strain diagram we have seen, and this is the true stress strain diagram. Now true stress strain means in the engineering stress strain diagram, this is kind of an approximation. So what is the approximation? Approximation means when we are calculating, you have seen that we are calculating only the force which is acting. Okay, we have actually measured what is the force that is acting on the big dial, and we measured with the help of extensometer what is the deformation that is taking place, right? And how we are converting the stress, simply what we are doing, that we have divided with the initial area that we have measured, and we are not considering the variation of area throughout the process of deformation. Similarly, we have considered the strain measurement as that all the strain, that means all the deformation taking place with respect to the initial length, which is not true, because the each and every moment you can understand that the deformation that is taking place with respect to that instantaneous length, not on the initial length. That is why definitely in the strain measurement as well as in the stress measurement there are error that is coming, and we actually have plotted with that error. So this is basically some kind of an approximated or erroneous curve. These are not the true stress strain curve, but we engineers prefer this curve, and I will explain why. And if you actually plot the true stress strain curve, you will see the true stress strain curve will deviate from the engineering stress strain curve in this way. Now let us understand, already I have told you that how engineering stress is defined, that is the load divided by the initial cross sectional area. Similarly, engineering strain is defined as the total elongation divided by the initial length. Now here you can see that this error will be very major, you can see in this region. Why? Because during necking the cross section changes in a very large rate, and since the cross section changing is not considered in the definition of the engineering stress, and that is why the curve or the true stress strain curve deviates from the engineering stress strain curve. Now then if the true stress strain curve is different from the engineering stress strain curve, then why engineers prefer drawing engineering stress strain diagram? There are two reasons. The first reason is that it is very difficult to continuously monitor the variation of the cross section. Okay, so this is the first point, and the second point is in most of the design problem we try to restrict our calculation within the elastic region, and you can see that true stress strain diagram and the engineering stress strain diagram within elastic region is same, that is not varying. But there are situations like when we are designing something related to manufacturing processes, forming, where a large deformation or the plastic deformation is important. In those situations, or the finite element design where high strain rate is involved, in those situations we need to know what is the true stress strain relationship or what is the true stress strain. So that is why it is important to know how can we find out the true stress strain from the engineering stress strain. So what is engineering stress, that we have already seen, and what is the true stress? In the true stress we have to consider the instantaneous area. So continuously the area is reducing in case of tension test. So that variation you have to consider if you want to find out the true stress. Okay, so let us try to find out a relationship between the true stress and the engineering stress. So this is what is the definition of the true stress. Now we know for the constant volume assumption. The constant volume assumption is that we are considering that within elastic region, when the deformation is taking place, the volume is not changing. This is an approximation. And the second one, this is also true in the plastic region. Okay, at least before necking, in the plastic region, this is true. Okay, so under this assumption that the volume is constant, volume is not changing, we can definitely write that at any instant the product of cross-sectional area and the length is equal to initial area and initial length. So from here we can simply write what is A. A is A naught L naught divided by L, and we put this value of A here, and if you do that, then what you will get, it will become FL by A naught L naught. Now what is this L by L naught? To find this L by L naught, already we know what is engineering strain. That is basically at any instant of time, if the length is L and L0 is the initial length, then this is basically what is the elongation, and that divided by the initial length, this is what is the strain we know, engineering strain. And if we write this, then it will be L by L0 minus 1. So what is L by L0? Definitely if this minus 1 go on that side, it will be 1 plus engineering strain. Now simply just put this L by L0 as 1 plus engineering strain, and this F by A0 already we know this is engineering stress. So that is why we can finally conclude that this engineering stress, the true stress is equal to engineering stress into 1 plus engineering strain. So if we know the engineering stress strain, we can find out the true stress. Now let us see what is true strain. Now let us consider a situation. Let us say this initial length is say L1. Suppose this length is L1, and with respect to L1 you can understand, if suppose delta L1 is the increment, then what is the strain? The strain is clearly delta L1 by L1. Now let us consider this L1 plus this delta L1. This quantity is say L2. Okay, so now it is the L2. Now from L2, let us consider again delta L2 deformation takes place. Then what is the strain here? So that delta epsilon 2 is basically the delta L2 that divided by L2. Similarly, now if you consider that L2 plus delta L2, that is L3, then from L3 you see if delta L3 takes place, exactly in a similar way you can see that delta epsilon 3 is equal to this. Now if we want to know from L1 up to this position what is the total strain, so actually the total strain is what? Summation of these three, delta epsilon 1, delta epsilon 2 plus delta epsilon 3. But this is what is the true strain. But in case of engineering strain, what we are doing is that we just finding out the total increment. That means if the final length is say L4, then what we are doing, this L4 minus L1 divided by L1. And you can understand that this quantity is not same as summation of these three, and that is why the true strain is different from the engineering strain. So to find out the true strain, what you have to do, you have to consider or you have to add all these instantaneous increments. So here we have shown it in a discrete way, but actually you have to do it in a continuous way. So for that the summation will be integration. Okay, so that integration will be from some initial length to L is basically the final length up to which you want to find out the true strain. And if you do that, the local increment will be with respect to that instantaneous length. Okay, so if you do this integration, the expression will be log of 1 plus L by L0, and put the value of L by L0 as 1 plus L by L0 is equal to 1 plus epsilon E. So you know that integration of this quantity is ln L by L0. Now just put the value of L by L0 as 1. So finally you can see your expression is that true strain is equal to ln 1 plus engineering strain. So if you know engineering strain, you can find out engineering true strain. So you can understand here that, remember that epsilon t, the true strain, is less than engineering strain. This is one of the thing we can see, because log of 1 plus x is x minus something and all that. So true strain is less than engineering strain, whereas definitely engineering true stress is more than engineering stress. That is true, that is clear from this one, because this one is a positive quantity. Now we'll see the torsion test. Now torsion test setup you can see, and the sample is first fixed between the holders, you see, and here you can see the two measurement device. This is one where you will get the value in Newton meter. This is basically the how much torque is applied, and here you can see one reading which is basically the indicates that how much revolution is taking place, and here there is a relationship that is given that one revolution is equal to 0.3 degree. Okay, so one revolution is equal to 0.3 degree. So here you can see this is the fixed end, this end is the fixed, whereas this end is actually rotating. Okay, with the help of some motor, this end is rotating, and here you will get the a number of revolution, and this number of revolution is related to the degree. So you will get the angle of twist of the sample. Okay, you can see gradually the amount of torque is increased, and that is why the amount of the degree is, or angle of twist is increasing. Because how to calculate the angle of twist? In the here from here we will note down what is the revolution, and we multiply that revolution with 0.3 degree, because the scale is one revolution is 0.3 degree. So in this way we will get the value of t and the angle of twist. So, and we can draw a diagram from the data as angle of twist and torque. And if we know t theta, then from that it is also possible to find out the shear stress strain diagram, because this torque is related to the shear stress and the angle of twist is related to the shear strain. Now let me show you. Here you see that this material is a brittle material that was taken, and you can see in this brittle material the fracture under torsion is taking place at an angle 45 degree. Now if we take a ductile material, you will find that there is a lot of plastic deformation, and finally you see the fracture that is taking place at that location, if you look carefully, and which is perpendicular. So let us try to see that why this has happened. Okay, but before that we have seen that we can find out theta from the experiment directly. We can read theta, and here you can see that if we can also read t, we can read theta. Length is the geometric thing that we can measure. J is the polar area moment of inertia that we can calculate for a circular section. We know it is pi by 32 into diameter to the power 4. So we can find out the modulus of rigidity or the shear modulus of the material directly. Okay, here you see that how the shear strain is related to the angle of twist. Okay, where rho is the radius and L is the length. here you see the shear stress, how it is related to the torque. So you can understand that these are the three important results that helps you to identify or find out the value of the shear modulus. This will help to relate or to find out the stress out of the torque and the shear strain from the angle of twist. This is the typical torsion stress strain curve. If you see that this is the plastic region, initially this is the elastic region, and here the fracture occurs, and the stress, shear stress corresponding to the fracture is what is called the shear strength. Okay, and that shear strength that we can find out from the torsion test. Now here is the fracture that we have seen, that cast iron we know is a brittle material, and you see that it's a 45-degree fracture that has been occurred, whereas this is a ductile material and the fracture taken place along the cross section. Now the reason is that already we have discussed that the ductile materials are weak in shear. So under torsion, if we draw the Mohr circle, you will find that the maximum shear is taking place at this location, and this location is where is the cross section. So that means along the cross section there will be failure. Okay. On the other hand, you see that in case of brittle material, you know that brittle material fails because of the tensile stress. Okay, because the crack can easily propagate under tensile stress, and where is the tensile stress maximum? It is clear in this Mohr circle. Here is the tensile stress maximum, and which is 90 degree in the Mohr circle, which means practically it is 45 degree in the real element. So at an angle 45 degree from the cross section, we have seen that the brittle material failed, and which we have observed in the torsion test. Now coming to the compression test. Now compression test, the basic setup is exactly same on the same universal testing machine, only the compressive load that we have to put on the sample, and again you can see the extensometer is there to measure the deformation load. You can measure from the dial gauge, and you can see the fracture that occurs in case of compression. In case of brittle material, you can see the fracture that has been taken place at an angle 45 degree. So if you draw the Mohr circle under compression, you see that uniaxial compressive load, when it is applied, there is no region where it is the tensile stress is present, and you know that brittle materials are weak in tensile stress. They cannot handle tensile stress, but there is no area where there is no region where the tensile stress is coming. So what happens basically in those cases, even brittle material fracture because of the shear, and the shear is maximum. Here you can see at an angle 90 degree from this location or this location. So actual element, it is the 45 degree. That is why this kind of shear failure of the cast iron you will observe. On the other hand, in case of a ductile material, you will find this kind of barreling of the ductile material. So this kind of a failure takes place, and after that some fracture marks may take place. Okay, but again remember the sample dimension is also plays a very important role. If the L by D ratio is large, in that case there is a possibility that if the sample may buckle. So the failure also may takes place because of buckling, okay, instead of fracture. That probably you have seen here, the buckling takes place on the sample. Now here you can see the typical stress strain diagram in compression test, and you can see for a steel sample the engineering stress strain diagram is now at the top, whereas the true stress strain diagram is at the bottom. And the reason you can understand because of the compression, actually cross sectional area actually increasing instead of decreasing, and that is why it is at the bottom. And you can exactly in a similar way can find out the ultimate stress point or the yield point. Okay, so this is what is the maximum point in the engineering stress strain diagram, where the this is corresponding to the compressive strength of the material. And at this point I just want to mention, you remember that in case of brittle materials, they are strong in compression. Okay, generally it is found that the brittle material having higher compressive strength with respect to tensile strength, whereas in case of ductile materials generally they have the in the similar order of the tensile and compressive strength. Now let us see this particular topic, generalized Hooke's law. Before that, let us first understand what is Poisson's ratio. So if we take this kind of a cuboid shape material, and let us consider that we are giving force, compressive force like this, and because of this force, you can see this particular axis along which the force is applied is called the longitudinal axis, and perpendicular to this longitudinal axis the other two axes which are called the lateral axis. And you can understand, when you are applying a compressive load like this along the longitudinal axis, in that direction the deformation will compress, right? On the other hand, in the other two lateral directions, you can see that the material actually elongate. Okay, now here you can see, if you apply tensile load on that sample, definitely in the longitudinal direction it will elongate, but in the other two lateral direction it will compress. Now here you can see that if the lengths of this cuboid shape is say Lx, Ly and Lz in three directions, then the deformation that is taking place because of this longitudinal load along the x direction, its elongation is delta x, and that divided by the initial length, which is Lx, is basically the strain along the x direction. So what is strain? So strain is basically the change in length divided by the original length, that we know. Now because of that, what will be the strain in the y direction? We have seen that in the y direction, instead of elongation, it is basically the compression takes place. So the amount of compression is minus of delta Ly, and that divided by the initial length in that direction. Similarly, in the z direction also compression takes place. So the epsilon y and epsilon z are the negative quantities because the compression takes place in those directions. Now see, we have seen that the epsilon y, basically this is the Poisson's observation that the strain in the lateral direction is proportional to the strain in the longitudinal direction, and this particular ratio is not changing during the deformation. Okay, so epsilon y by epsilon x is a constant. Okay, if it is an isotropic material, maybe epsilon z by epsilon x is also same with epsilon y by epsilon x, and this ratio is a material constant which is called the Poisson's ratio. So Poisson's ratio is what? To make this quantity positive, one negative sign is put here, and you can see it is the strain in the lateral direction divided by the strain in the longitudinal direction. But we know that the strain in the lateral direction will be a negative. That is why another negative is put, so that this Poisson's ratio become positive. In most of the practical situations, you know that if you elongate, the material will compress in the lateral direction. So keeping that thing in mind, basically this negative sign is given to make this Poisson's ratio positive. So you will find most of the practical materials, the Poisson's ratio are between 0 to 0.5, and you can see the typical values are like steel and copper. You can see the Poisson's ratio is in the order of 0.3. In case of aluminium, it is slightly more, 0.35. In case of concrete, it is 0.2, and in case of rubber, it is 0.5. The significance of the 0.5 Poisson's ratio is that there will be no change of volume. Only the shape will change, but there will be no change of volume. And the Poisson's ratio is exactly equal to 0. The meaning is that you are giving Here you see in this picture, you are giving some tensile load. What is happening? It is elongating at that direction, but in the y direction nothing is changing. So in the y direction there is no deformation, only in the x direction it is deforming. Very few materials falls in this category. One of the example is the cork. Okay, so you can see that cork having that property, you are giving the compressive load but its diameter is not increasing, and that is why this is suitable to fit within bottle cap. Now see another example which is also possible in some of the engineering materials like foam. Foam is the example where it is possible that the Poisson's ratio will be negative. What is the meaning of the negative Poisson's ratio? That means you are giving the tensile load, suppose in the longitudinal direction, but what will happen at the same time in the lateral direction also the cross section will increase. So which is apparently looks impractical, but some of the engineering materials having this property like foam, and you can see that how this can happen because of the internal structure. Here you can see if you give the compressive load, because of the structure this kind of bending will occur, and you observe carefully in the other lateral direction it is also decreasing. Okay, so these are the materials where the Poisson's ratio is negative. But most of the materials, most of the commonly known materials, Poisson's ratio should be between 0 and half. Now coming to the strain components under uniaxial loading. Suppose sample is under uniaxial loading, and if you take that sample, kind of stress that is acting is sigma x, then what is the strain? It is clear that this direction is the x direction. So along x direction its strain will be equal to sigma x by E, because we are considering it is the proportional relationship between stress and strain that we have already seen in a stress strain diagram within elastic region, right? So strain will be equal to sigma x by the modulus of elasticity, or the Young's modulus. Now in the y direction, what will be the strain? In the y direction, we have already seen the definition of Poisson's ratio, that it will be epsilon x into Poisson's ratio, and the negative sign you have to put, because that is what is the definition of the Poisson's ratio, that epsilon y with a negative sign by epsilon x. And similarly epsilon z will be this one. Okay, so in this way for uniaxial loading we can find out the strain in 3 different directions. But let us consider, instead of uniaxial loading, suppose load is there in all 3 axes, then what will happen? If load is there in all 3 x, y and z axes, in that case remember that epsilon x will not be only sigma x by E, because in the y direction, this is the y direction, in the y direction there is stress sigma y, right? So because of that sigma y, definitely there will be longitudinal strain in the y direction, and that is sigma y by E. But because of that strain, we know that in the with respect to y axis in the lateral direction there will be compression, and that compression will be what? The Poisson's ratio multiplied by the Poisson's ratio. Okay, so this will also affect separately on the x axis, so that you have to consider what is happening because of sigma y. Now similarly in the sigma z some stress is there, and because of that the strain, longitudinal strain, will be sigma z by E, and because of that strain the Poisson's ratio, the negative sign, this particular thing will act again in the x direction. So that also you have to consider. Okay, so the superposition of these 3 if you do, then you will get the total strain that will act in the x direction. So first one is the direct strain, longitudinal strain because of sigma x, and these 2 are corresponding to the lateral strain because of sigma y and sigma z. So if you just simply rearrange taking common 1 by E, you will get this kind of a relationship, and exactly the similar thing you can do for the Y and Z direction. And this set of equations, that the stress strain relationship when in the 3 direction sigma x, sigma y, sigma z present, at that time the stress strain relationship is what is called the generalized Hooke's law. Thank you.